Understanding ampacity calculations for three-phase panels is crucial for safe and compliant electrical installations. It's important to clarify some misconceptions about how to determine the maximum allowable current in such systems and how to correctly size conductors. The initial reasoning of multiplying the panel amperage by the number of phases and then applying an adjustment factor is not entirely accurate. The adjustment factor is applied to the conductor ampacity, not directly to the panel rating in that manner. Let's break down the correct method for determining the allowable current and conductor sizing. The ampacity of a three-phase panel refers to the maximum current that the panel's main breaker or busbars are rated to handle. In a 100 amp three-phase panel, the main breaker is designed to trip if the total current exceeds 100 amps, regardless of how it's distributed across the phases. The misunderstanding arises when trying to correlate this panel rating with the allowable current for individual conductors. The key is to correctly size the conductors feeding the panel and the branch circuits based on the loads they serve, while respecting the panel's overall ampacity. Now let's address conductor sizing and the application of adjustment factors. When determining the appropriate wire size, you must consider the ampacity of the wire, the ambient temperature, and the number of current-carrying conductors in the raceway or cable. The National Electrical Code, or NEC, provides tables that list the ampacity of conductors based on their size and insulation type. For example, using copper conductors and referring to the 75 degrees Celsius column in NEC table 310.15b16, a number 2 copper wire typically has an ampacity of 115 amps. However, this ampacity must be adjusted if there are multiple current-carrying conductors bundled together. When conductors are bundled, the heat generated by each conductor can raise the overall temperature, potentially exceeding the insulation's rating. To compensate for this, the NEC requires the ampacity to be reduced using adjustment factors specified in NEC table 310.15 cone. For example, if there are 4 current-carrying conductors in a raceway, the ampacity must be derated to 80% of its original value. In the case of the number 2 copper wire with an initial ampacity of 115 amps, multiplying by the 0.8 adjustment factor results in a final ampacity of 92 amps. Therefore, with 4 current-carrying conductors, a number 2 copper wire can safely carry 92 amps. It's permissible to protect this conductor with a 100 amp breaker, as the breaker's purpose is to protect the wire from overcurrent. As long as the conductor's adjusted ampacity is not less than the non-continuous load plus 125% of the continuous load, and the overcurrent protection device is not rated higher than the conductor's ampacity after derating, you are in compliance with the NEC. Now, considering single-phase loads connected to a three-phase panel, it's crucial to distribute these loads as evenly as possible across the 3 phases to maintain balance. An imbalanced load can lead to voltage imbalances and increased current in some phases, potentially overloading the panel or conductors. To ensure proper load balancing, use a load calculation worksheet to determine the total load on each phase. Then, distribute the single-phase load so that the current draw on each phase is as close as possible to the average. Remember that each single-phase load will require a single pole breaker connected to one of the 3 phases. The size of the breaker should be appropriate for the load and the conductor size, following NEC guidelines. Here's a step-by-step recap for calculating conductor ampacity and breaker size. Firstly, determine the total load in amps that the circuit will carry. This includes both continuous and non-continuous loads. Secondly, apply any applicable derating factors based on the number of current-carrying conductors, ambient temperature, or other conditions as specified in the NEC. Thirdly, select a conductor size that has an ampacity equal to or greater than the adjusted load current. Use the appropriate NEC table based on the conductor type and temperature rating. Fourthly, choose a breaker size that is appropriate for the conductor size and the load. The breaker should protect the conductor from overcurrent but should not be larger than the conductor's ampacity after derating. The NEC also has specific rules regarding breaker sizing, so be sure to consult the relevant sections. To further clarify, let's consider a scenario. Suppose you have a 3-phase panel supplying power to several single-phase loads, including lighting, receptacles, and small appliances. The total calculated load on phase is 80 amps, on phase B is 75 amps, and on phase C is 90 amps. The conductors feeding these loads are number 2 copper wires with 4 current-carrying conductors in a raceway. We've already established that the number 2 copper wire, when derated to 80%, has an ampacity of 92 amps. Therefore, the number 2 copper wire is suitable for all 3 phases, as the load on each phase is less than the wire's adjusted ampacity. You can use 100 amp breakers to protect each of these circuits, as long as the load on each circuit does not exceed 80% of the breaker's rating for continuous loads. Remember, continuous loads are defined as loads that operate for 3 hours or more at a time. In summary, the gentleman's initial calculation was incorrect because it misapplied the adjustment factor. The correct approach is to determine the conductor ampacity based on its size and insulation type, apply any necessary derating factors, and then ensure that the breaker size is appropriate for the conductor and the load. Load balancing across the 3 phases is also essential for efficient and safe operation. Understanding these principles and following the NEC guidelines will ensure that your electrical installations are safe, reliable, and compliant. Always refer to the latest edition of the NEC and consult with a qualified electrician if you have any questions or concerns. Remember, working with electricity can be dangerous, so always take precautions and follow safety guidelines. When dealing with electrical systems, accuracy and adherence to safety standards are paramount. Understanding the proper application of ampacity adjustments, conductor sizing, and load balancing is crucial for safe and efficient electrical installations. Incorrect assumptions and shortcuts can lead to hazardous situations, including equipment damage, fire, and electrical shock. Always consult the latest edition of the NEC and seek guidance from experienced and licensed electricians to ensure compliance and safety. Let's delve further into the nuances of conductor ampacity and correction factors. The NEC provides detailed tables and guidelines for determining the allowable ampacity of conductors under various conditions. These tables take into account factors such as conductor material, insulation type, ambient temperature, and the number of current-carrying conductors in a raceway or cable. For example, NEC Table 310.15b16 lists the ampacity of insulated conductors rated up to 600 volts, based on the conductor's size and temperature rating. It's crucial to select the correct ampacity based on the specific conditions of the installation. Ambient temperature is another critical factor that can affect conductor ampacity. The NEC specifies correction factors that must be applied when the ambient temperature exceeds the temperature rating of the conductor's insulation. For example, if a conductor with a 75 degrees Celsius insulation rating is installed in an environment with an ambient temperature of 40 degrees Celsius, a correction factor must be applied to reduce the conductor's ampacity. These correction factors are listed in NEC Table 310.15b2. The number of current-carrying conductors in a raceway or cable is another significant factor that affects conductor ampacity. When multiple conductors are bundled together, the heat generated by each conductor can raise the overall temperature, potentially exceeding the insulation's rating. To compensate for this, the NEC requires the ampacity to be reduced using adjustment factors specified in NEC Table 310.15 cone. These adjustment factors vary depending on the number of current-carrying conductors. For example, if there are 4 to 6 current-carrying conductors in a raceway, the ampacity must be derated to 80% of its original value. It's important to note that the neutral conductor in a 3-phase, 4-wire system is generally considered a current-carrying conductor. However, if the load is primarily nonlinear, such as with electronic equipment, the neutral conductor may carry significant harmonic currents, and its ampacity must be adjusted accordingly. In addition to ampacity adjustments, the NEC also specifies requirements for overcurrent protection. Overcurrent protection devices, such as circuit breakers and fuses, are designed to protect conductors from overloads and short circuits. The size of the overcurrent protection device must be appropriate for the conductor's ampacity and the load it serves. The NEC generally requires that the overcurrent protection device not exceed the conductor's ampacity after all applicable directing and correction factors have been applied. However, there are some exceptions to this rule, such as when the conductor is supplying a motor load. In such cases, the overcurrent protection device may be sized larger than the conductor's ampacity to allow for motor starting currents. It's crucial to carefully consider the specific requirements of the NEC when selecting overcurrent protection devices to ensure adequate protection and compliance. Load balancing is another critical aspect of three-phase power systems. Unevenly distributed loads can lead to voltage imbalances, increased current in some phases, and reduced system efficiency. To minimize these problems, it's essential to distribute loads as evenly as possible across the three phases. This can be achieved by carefully planning the distribution of single-phase loads and by using three-phase equipment whenever possible. Load balancing can also be improved by using power factor correction capacitors to reduce reactive power and improve the overall power factor of the system. In summary, understanding the principles of conductor ampacity, correction factors, overcurrent protection, and load balancing is crucial for designing and installing safe and efficient electrical systems. The NEC provides detailed guidelines and requirements for these aspects, and it's essential to follow these guidelines to ensure compliance and safety. Always consult the latest edition of the NEC and seek guidance from experienced and licensed electricians when working with electrical systems. Remember, electrical work can be dangerous, so always take precautions and follow safety guidelines.